We throw around words like temperature and energy pretty much every day. But what if I told you they don't actually mean the same thing? In physics, the difference is absolutely huge, and it explains some really weird counterintuitive things about the world around us. So let's find out why what you feel isn't always the full story.
Okay, to kick things off, let me throw a little puzzle your way. Picture this. You've got a tiny teacup and it's steaming hot, like 80 degrees Celsius. And right next to it, there's a huge bathtub filled to the brim with nice, warm water, maybe 40 degrees Celsius. The question seems simple enough. Which one has more energy? Now, your gut might immediately say the teacup, but, well, let's see. Now, this slide asks a slightly different question. Which one has greater average kinetic energy? Kinetic energy is just a fancy way of saying the energy of motion. So what this is really asking is, in which of these are the water molecules jiggling around faster on average? Well, since the teacup is hotter, its molecules are definitely moving faster. So that seems like an easy win for the teacup. But that word average, that's a big clue that we're not getting the whole story here. So yeah, that's our puzzle. The super hot teacup versus the big, warm bathtub. Let's start breaking it down. That one little word, average, that's the key to everything here. It's a huge hint that there's another piece to this puzzle that we're missing. I mean, if temperature only tells us about the average, what is it leaving out? To really solve this, we've got to get a handle on the difference between average energy and total energy. Trust me, once you get this, everything else just clicks right into place. Okay, so first up, temperature. When you stick a thermometer in something, what are you actually measuring? You're measuring the average speed or the average kinetic energy of all the teeny tiny molecules in that thing. So a high temperature just means the molecules are, on average, zipping around really fast. A low temperature means they're moving a lot slower, again, on average. And that brings us to the other side of the coin, thermal energy. See, this has nothing to do with the average. Thermal energy is the sum, the total kinetic energy of every single molecule in that sample, all added up together. So here's the crucial bit. It's not just about how fast the molecules are moving, but also about how many of them there are to begin with. You know what? To make this difference super clear, let's put the teacup and bathtub aside for just a minute and look at a whole new mystery. I call it the case of the two soups. Let's say it's a cold day. You pour some soup for yourself and your little brother, all from the same big pot. You get a nice big bowl and he gets a small mug. Now, because it all came from the same pot, both servings start at the exact same temperature. That means their molecules all have the same average energy. So far, so good. But the soup's a little too hot to eat. So you decide to do a little experiment. You grab 2 identical ice cubes from the freezer and you drop one into your big bowl and one into his small mug. Everything's the same. Same soup temperature, same ice cubes. What do you think is going to happen next? A few moments later, your brother takes a sip and complains, "Mine's cold." But you try yours and it's perfect, still nice and warm. How is that even possible? You added the exact same ice cube to both. Now we have a real mystery on our hands. Why in the world did his soup get so much colder? Well, here's the big clue. The only thing that was different was the amount of soup. Your bowl had way more of it, which means it had way more molecules than the little mug. And that one simple fact, well, it changes everything. All right, so we've got all the pieces. We know the difference between average and total energy, and we know the bowl had way more molecules. Let's solve this thing. This slide really breaks it down with some simple math. Think of thermal energy as step 1. You just add up the energy of every single molecule to get one big total. Temperature, on the other hand, is like step 3. You take that total and then you divide to find the average. They're connected, for sure, but they are totally different concepts. So let's walk through the solution. Both soups started at the same temperature, which means they had the same average energy. But your big bowl, with its millions and millions of extra molecules, had a much, much higher total thermal energy. Now, melting an ice cube takes a specific amount of energy. For your big bowl, losing that bit of energy was like taking a single dollar from a millionaire. They'd barely even notice. But for the small mug, it was like taking a dollar from someone who only has $2. That's a huge loss. And it caused its average energy, its temperature, to drop like a rock. And now, finally, we can go all the way back to our original puzzle. The bathtub, even though it's much cooler, is just like that huge bowl of soup. It has trillions upon trillions more water molecules than that little teacup. So when you add up the energy of all those molecules, the bathtub has way, way more total thermal energy than the tiny hot teacup. Puzzle solved! So this isn't just some fun brain teaser. This difference between temperature and thermal energy has massive real-world consequences. We're talking major engineering problems. Take a look at this. It's a real-world problem. To heat an entire school, engineers might have two choices: a small tank of very, very hot water or a huge, stable source of cooler groundwater. Sound familiar? It's our teacup and bathtub puzzle, just on an industrial scale. So, which option can actually deliver more heat to the school? See, what it all comes down to is this. To heat the air in the school, you have to transfer energy to the air molecules. The question isn't just about which water source is hotter. The real question is, which system is holding more total thermal energy that it can give away to the school? So this leaves us with one last big question. What really matters for heating something up? The intensity of the heat, its temperature, or the sheer amount of energy it has available, its thermal energy? As we've seen, the answer isn't always what you'd think. It affects everything from how we heat our homes to the incredible power stored in our oceans. It turns out, sometimes the warm bathtub is mightier than the hot teacup. Thanks for joining this explainer.